Okay, so now there are only a couple of things left here from the theory related to these hyperbolas. So far we have derived the standard equations. We have derived these standard equations of basically hyperbolas, and basically you know that these equations basically are only two cases of hyperbolas, where basically in one case we had the transverse axis along the x-axis, and the center of the hyperbola was the origin of the coordinate system, in which case basically we got x squared by a squared minus y squared by b squared is equal to 1. And in the other case we had basically the hyperbola kind of rotated 90 degrees counterclockwise, and the transverse axis of the hyperbola was along the y-axis of the coordinate plane, and the center of the hyperbola was exactly the center of the coordinate system, in which case we got basically y squared by a squared minus x squared by b squared is equal to 1. So these are just two cases of these hyperbolas, and of course you know that the transverse axis, as far as a hyperbola is concerned, you always have the transverse axis over here. And then you have the conjugate axis. So this is the conjugate axis. You have the conjugate axis over here. You have the transverse axis over here. And basically your foci, the foci of the hyperbola are always on the transverse axis, meaning that, for example, you could take this as f2, and for example take this as f1, and then the vertices of the hyperbola would be somewhere, for example, over here, would be somewhere between the center and one of the foci. For example, this would be your the vertices, and so you would have a hyperbola something like this. So this thing over here, what you can see here, you can imagine that you can consider this as a system. As a system, you can consider this as hyperbola, meaning that the hyperbola, irrespective of whether you want to represent it in a 2D plane, or if you want to represent it in a 3D plane, or whatever sort of plane you might have, it's a conic section consisting of basically this system that you can see over here. You have a conjugate axis, you have a transverse axis, the axes are perpendicular, you have a center over here, you have these two vertices over here, you have these two foci over here, and that's basically the whole system. Now we can take this system and put it in a 2D plane, in a 2D coordinate plane, which would be basically in which you would have an x-axis and a y-axis over here, and then you could basically put your center on the center of the coordinate system. You could put the transverse axis across the x-axis. You could keep the center over here, put your transverse axis across the y-axis, or you could do any other orientation of this whole system in this plane, meaning that you can just keep moving it in any way that you want. You could put the center, for example, over here, and then the system would basically looks at something like this, and then your hyperbola would be something like this. So you could do anything that you want. So basically these, what I mean to say is that basically these two cases that we showed over here, this case and this case, are just two very, very general cases and very basic cases of these two hyperbolas. And we are not going to talk any further about any, basically we are not getting any, we are not going to talk about any more advanced stuff than this, more advanced cases than these two right here. I suppose probably in the next book there will be some more advanced cases of these hyperbolas, but then basically it gets a little more serious in the first year of university. For example, if you do an engineering course or something that has to do with mathematics, then over there we will actually study this in more detail. But I mean, further than this would be beyond the scope of what we are doing right now, because over here we are doing just very simple basic mathematics, and then after that we will get into more detail about each of the things that we do over here. Now, of course, you know that from the standard equations of the hyperbolas that we derived, you know that the hyperbola is, of course, basically, number one, a hyperbola is basically symmetric with respect to both the axes, And you know basically what that means is that basically, for example, if you have some hyperbola over here, imagine that I put the transverse axis along the x-axis and the conjugate axis along the y-axis, and if I did so, I would get basically something like this. And then let me quickly draw these two lines as well, so that and then let's do a simple so let's say that this is the hyperbola that we have. So if this is the hyperbola that we have, and this is, for example, suppose that this is, for example, f1 and this is f2. Now if you pick any point over here, for example, if you pick this point over here, call it p x comma y, then basically, since your hyperbola is of course symmetric with respect to the y-axis, or I would say the vertical axis. In this case, it could be the conjugate axis or the y-axis. if you basically draw a line perpendicular to the y-axis and then go the same distance in the same direction, you will get to some point on the hyperbola where the coordinates of that point is. For example, if I call this P1, this would be P2 with coordinates basically x2, for example. That would be basically, the coordinates would actually be the same y but negative x comma y. And since again your hyperbola is symmetric with respect to the x-axis as well, if I drop a perpendicular to the x-axis and go to the same distance in the same direction, I will get to this point where I can call it P3, and over here I will have the same x but negative y over here. And if I have the same point over here, since again I'm symmetric with respect to the y-axis, perpendicular to the y-axis the same distance, and I will get to some point over here which I can call P4 with the same y, negative y, but then the algebraic opposite of this x, meaning that I will get x, basically x negative y over here and negative x and negative y and so on and so forth. So that means that if P, for example, with coordinates x comma y is on a hyperbola, then the points basically negative x comma y, negative x comma negative y, and x comma negative y are also going to lie on the hyperbola, and that is basically called symmetry. So that is basically one thing. And there is something about the foci. So the foci, basically these 2 points over here, F1 and F2. Let me do it with some other color so that you can see it. So F1 and F2, the foci are always on the transverse axis. Now whether you basically happen to basically align the transverse axis with the horizontal axis in the plane or the vertical axis in the plane or in any other orientation, but the foci are always on the transverse axis, are always over here. And basically we said that for example, if your hyperbola in this orientation, then the formula for the equation for that would be x squared over a squared minus y squared over b squared is equal to 1. And you see the positive term over here is this. This is the positive term. I mean the term that basically you have basically two terms over here, the term that contains the x and the term that contains the y. And in each case one of these terms is going to be positive. So now the positive term is x, and the denominator of this the denominator of this term is going to give you the transverse axis, because over here, as you can see, x squared by a squared, so the denominator is a squared. So whatever a squared over here is, then you can take the square root of that, and then we said that basically the length of the transverse axis, the length of the transverse axis was the length of the transverse axis was I suppose it was 2a. It was basically, let me go over here and check out. I don't really remember. The length of the transverse axis. So we said that we denote the distance between the two foci by 2c. The two foci by 2c, the distance between the vertices, the length of the transverse axis by 2a. So, okay, so basically the length of the transverse axis is basically this distance over here. So this is the length of the transverse axis, which is denoted by 2a. So then basically you can figure out what your a is from here, and then basically take the square root of a squared and then multiply it by 2, and that gives you the length of the transverse axis basically. So that is that. So then it just depends on the kind of equation that you have. It just keeps changing. But again, for example, if you had your hyperbola in the other orientation that we had, we said that basically you have y squared by a squared minus x squared by b squared is equal to 1. And again, over here you can see that the positive term is this term over here, not this term. The positive term is over here, and basically again the denominator is, in this case, is a squared. So you can take this denominator, take the square root of that, multiply it by 2, and that is basically the length of the transverse axis, which is equal to 2a, which is equal to the distance between the vertices, of the hyperbola. Now there is only one thing left here, which is the Latus Rectum of the hyperbola. We will discuss this over here as well, and then we have some examples. So the Latus Rectum of a hyperbola, let me see if we can, no, this is too crowded. Okay, so let's say that you have this hyperbola over here. This is, for example, the conjugate axis, so let's call it y, let's call this x, and I'm going to have this distance over here and this distance over here, and then I'm going to draw these lines as well. And then we can basically draw some sort of hyperbola over here, something like this. and something like this. So let's say that this is your hyperbola, and this point over here are your foci. Let's call this, for example, F1 and F2. So this line segment over here, which is perpendicular to the transverse axis, and the endpoints of that line segment lie on the hyperbola itself, and it is perpendicular to the transverse axis and passes through the foci. Any of the foci is called the Latus Rectum. It's called the Latus Rectum of the hyperbola, and the length of this line over here is nothing but the length of the Latus Rectum of an ellipse. The length of the Latus Rectum of an ellipse was equal to 2 times b squared by a. And as it turns out, the length of the Latus Rectum of a hyperbola is also the same thing, 2b squared by a. That's the same thing basically. So that's basically that. Now we have a couple of questions over here. 1, 2, 3. Only 3 questions over here, and then we have some exercises related to these hyperbolas. So I'll take a few minutes rest and we will do the 3 questions together. Okay, so the first exercise or example that we have over here is you want to find the coordinates of the foci, and basically F1 and F2, and the vertices, and basically V1 and V2, and the eccentricity E, and the length of the Latus Rectum LR of these hyperbolas. So suppose that the hyperbolas that you have are, for example, x squared by 9 minus y squared by 16 is equal to 1. So basically the equations of the hyperbolas that we had were basically either x squared by a squared minus y squared by b squared was equal to 1, or it was y squared by a squared minus x squared by b squared is equal to 1. So now you can see that over here, basically your y is the negative term. So that means that it's basically this first equation over here. So that means that I can compare this equation to this equation. So I can write x squared by a squared minus y squared by b squared is equal to 1. And if I compare here, I can see that basically a squared is equal to 9, and a squared is equal to 9, and b squared is equal to 16. Now the basically the coordinates of the foci F1 and F2, basically your foci are at basically are C units away from the center, meaning that you're at basically plus or minus C, 0 basically are going to be the coordinates of your foci, meaning that F1, for example, would be basically C, 0, and F2 would be negative C, 0. So to find basically the coordinates of the foci, I need C over here, which I don't have. I need to calculate that. The coordinates of the vertices would be basically, the vertices are A units away from the center. So that's plus or minus A, 0. So that means that, for example, V1 would be A, 0, and V2 would be negative A, 0. The eccentricity would be equal to C divided by A, meaning that for this I do need basically C and A. I have already A over here, but C I need to calculate it. And the length of the lattice rectum, is basically 2 times B squared by A, which basically we can calculate based on what we have over here. So if I calculate my C over here, I'll be able to calculate all of these things over here. So there was a relationship between A, B, and C, and that was the square root of C. The square root of C was the square root of C was the square root of B. We said that basically the square root of B is equal to the square root of C squared minus A squared. That means that B squared is equal to C squared minus A squared. So basically what that means that C squared is equal to B squared plus A squared. C squared is equal to B squared plus A squared. So C squared is equal to B squared, which is equal to 16, plus A squared, which is equal to 9, which is equal to 25. So over here your C squared is equal to 25. So then I can say that and so that means that basically C is equal to basically the square root of 25, which is equal to 5. So your C is equal to 5, your B is equal to 4, and your A is equal to 3. Now your foci are at basically F1 is at C, 0, so that's 5, 0, and negative 5, 0. Your vertices are at basically A, 0 and negative A, 0, so 3, 0 and negative 3, 0, negative 3, 0. Your eccentricity is equal to C divided by A, which is 5 divided, that is 5/3. And the length of the lattice rectum would be equal to 2 times B squared, 2 times 16 over A, which is equal to 3, so that's 32 thirds units. So that's basically all the information that we need here. So now let's go back to the example and see So your A is equal to 5 32/3 plus or minus 5. The foci, the vertices, and that's basically all the information that we have, that we need. So the next question that we have is basically we have another basically another hyperbola, which is y squared minus 16x squared is equal to 16. So you need to write this either in the form, basically you need to write this either in the form x squared by a squared minus y squared by b squared is equal to 1, or you need to write it in the form y squared by a squared minus x squared by b squared is equal to 1. Now, when you start writing it, it will automatically basically be any of these two forms. You will see about that. So then, if I divide this equation by 16 to get a 1 over here, I will get y squared over 16 minus 16 x squared over 16 is equal to 16 over 16. So that means that this is y squared over 16 minus x squared, which you can write as x squared over 1 is equal to 1. So basically you can compare this equation to the second equation over here, meaning that you can compare it to y squared over a squared minus x squared over b squared is equal to 1. And now if you compare it, you'll see that basically a squared is equal to 16 and b squared is equal to 1. And we said that over here b is equal to square root of c squared minus a squared. We said that b is equal to square root of c squared minus a squared. C squared minus a squared. And so that means that b squared is equal to c squared minus a squared. Here I want to calculate c. So c squared is equal to b squared plus a squared. So c squared is equal to b squared plus a squared is 17. So that means that your c squared is equal to 17. Now, the next thing that we need is basically now let's go for the coordinates of the foci. The coordinates of the foci are at a distance c away from the center. That means that f1 would be basically negative c comma 0, which would be, for example, so if basically c squared is equal to 17, then c would be equal to the square root of 17. So negative square root of 17 comma 0, and f2 would be basically c comma 0, which is the same thing as basically c comma 0, which would be the square root of 17 comma 0. These are your foci. Your vertices would be v1, for example, a comma 0, which would be basically 4 comma 0, and v2 would be negative a comma 0, which is basically negative 4, 0. Now your eccentricity E is equal to C divided by A, which is equal to the square root of 17 divided by 4, square root of 17 divided by 4, and the length of the latus rectum, is equal to 2 times B squared by A, which is equal to 2 times B squared is equal to 1, which is 2 times 1 is equal to 2. A is equal to 4, 2/4, which is equal to 1/2. So then basically C is the square root of 17, and foci are at 0, oh, we have made a mistake over here. You see, I have to be careful about this thing over here, which we made a mistake, and that's basically a good mistake to make, because you can catch yourself. What that means is that of course C, A squared, B squared, C squared, these are correct. There is nothing wrong with that, but it is always helpful to have a diagram. So basically we said that when y squared becomes the positive term, your not the major axis but the transverse axis, your foci and everything are along the y-axis. What that means is that of course basically, for example, when you want to write your foci, for example F1, that would be at a distance of C away from the center, but in this direction, meaning that your foci would be basically 0, for example C, and F2 would be, for example, 0, negative C. Your vertices V1 would be, for example, again along the same line, 0, A, and your V2 would be again the same thing, 0, negative A. But of course there is no problem with the eccentricity. Your eccentricity is basically the same thing as you would do if basically you had the other form of the equation, meaning that your C is equal to your E is equal to C to A, which is equal to basically the square root of 17 to your A is equal to 4, your B is equal to 1. So C divided by A is equal to square root of 17 to 4. Square root of 17 to 4. And the length of the latus rectum, would be the same thing, 2 times B squared by A, which is equal to 2 times B squared, which would be 2 times 1 is equal to 2. A is equal to 4, 2/4, which is equal to 1/2. But about these 4, your F1 would be basically 0, square root of 17. Your F2 would be 0, negative square root of 17. Your V1 would be 0, 4, 0, 4, and your V2 would be 0, negative 4. Which is, and this is actually the correct answer. you need to be careful about, and basically always a diagram is very, very helpful. Okay, so the next question that we have is question number 15. So the next question that we have is, you want to find the equation of the hyperbola. You want to find the equation of the hyperbola with foci 0 plus or minus 3 and vertices 0, plus or minus square root of 11 by 2. You want to find the equation of this hyperbola. So as you can see, these points are all along the vertical axis, meaning that basically your transverse axis is along the y-axis. So you do need to use the equation y squared by a squared minus x squared by b squared is equal to 1. Now, since the foci are at these points, then of course you know that basically your c is equal to 3. Your c is equal to 3 because the foci are at a distance c away from the center, and since the vertices have these coordinates, you know that your a is equal to square root of 11 by 2 because the vertices are a units away from the center. So now over here I have a and c, I need b over here. So I keep forgetting that formula. So basically my problem is that if I don't derive something in mathematics, if I don't know where it comes from, then I can't remember it because I'm not very good at memorizing things. I can learn things, but I cannot memorize things. That's my. I guess I should work on that probably. So then we said that basically b is equal to the square root of c squared minus a squared. And so if that is the case, that means that b squared is equal to c squared minus a squared. And since I want basically, so then b squared is equal to c squared, which is equal to 9, minus basically 11 by 4, which is equal to 4 times 9 is equal to 36 minus 11, which is equal to 25 fourths, which is equal to 25 fourths. So what that means is that b squared is equal to 25 fourths. Now, so I can basically write this equation as, then I can write it as y squared by a squared, which is basically this fraction whole squared, which is 11 divided by 4, minus x squared by b squared, which is 25 by 4 is equal to 1. Now what you can do is that, but to simplify this, basically you have some, let's say that you have some number over here, some a, for example, divided by b divided by c. So you can write this as a times c by b, a times c by b. So then you would write this thing, for example, y squared by 11/4. You would write it as y squared times 4/11, which would be basically 4y squared over 11. 4y squared over 11. And this would be 4x squared over 25. 4x squared over 25. I'm trying to find the best way to simplify this, to simplify this equation. Now let me see how they have written this equation over here. They have just simply written it in this form, so I'm going to just do the same thing, meaning that you can write this as 4y squared by 11 minus 4x squared by 25 is equal to 1. And then what I'm going to do is that multiply this by 11 times 25, so 4 times 11 times 25 over 11, and if we have y squared over here, minus 4 times 11 times 25 times x squared, and divide by 25 is equal to 4 times 11. So then that is equal to, so 11 and 11 you can cancel out, 25 and 25 you can cancel out. 4 times 25 is equal to 100, so 100y squared minus 44x squared is equal to this was 11 times 25, I'm sorry. This was 11 times 25. So 25 times 11 is equal to 25, 25. That's 275. 275, and that is your equation there. So the next question that we have is, find the equation of the hyperbola. Find the equation of the hyperbola where foci are 0 plus or minus 12, and the length of the lattice rectum is equal to 36 units. 36 units. Okay, so you see that your foci are along the y-axis. So that means that you want to use this equation y squared by a squared minus x squared by b squared is equal to 1. And since your foci are C units away from the center, so that means that your C is equal to 12. Your C is equal to 12. Now the length of the latus rectum is 2b squared by A is equal to 36 units. And so I can simplify this as 18. B squared by A is equal to 18. And then we have some other relationship between AB and C, which is B is equal to C, which is B is equal to basically the square root of C squared minus A squared. So that means that B squared is equal to C squared minus A squared. So what that means is that, so since I know what C is, I can substitute it here. I can write B squared is equal to basically C squared, which is equal to 144 minus A squared. So I have this equation over here, which is B squared by A. B squared by A is equal to 18. Call this equation number 1. And I have B squared is equal to 144 minus A squared. Call it equation number 2. So using these two equations, I can find A and B. So now what I'm going to do is that I'm going to write this equation as B squared is equal to 18A. That means that A is equal to B squared by 18. B squared by 18. B squared is equal to 18A. That means that A is equal to B squared by 18. If I put that over here, if I put this over here, I will get some. Well, what I'm going to do is that I'm just simply going to use this equation directly, because otherwise I would get a 4th degree equation. That would be a lot of trouble. So then I'm going to use this equation over here. Instead of B squared, I'm going to write 18A is equal to 144 minus A squared. So now I have negative A squared, negative 18A plus 144 plus 144 is equal to 0. Negative A squared, negative 18A plus 144 is equal to 0. Or I can write A squared plus 18A minus 144 is equal to 0. Now, to solve this equation, you can write 144 as basically 2 times 72, 2 times 36, 2 times 18, 2 times 9, so this is 16 and 9. This is 9, this is 3 times 3. 16 times 3, no. 8 and 18, no. Okay, so I think the best way when it comes to these equations, sometimes when the number is too large, it's not easy to factorize it. So what you want to do in such situations is that write it, for example, as a squared plus 2 times a times basically 2 times 8 times, for example, 9. So this is 18a, and this is going to give me unreal roots. There must be something wrong over here. So over here we have b squared by a is equal to 18, and here we said that b squared is equal to the square root of c squared minus a squared. That means that b squared c squared minus a squared, b squared is equal to c squared, which is equal to 144 minus a squared. So b squared is equal to 144 minus a squared. Now that means that then over here I have b squared is equal to 18a. So b squared is equal to 144 b squared is equal to 144 minus a squared. 18a is equal to 144 minus a squared. And then what that means is that negative a squared, negative 18a plus 144 is equal to 0, or a squared plus 18a minus 144 is equal to 0. And that doesn't give me real roots. That's but the equation is right. There's nothing wrong with the equation. So let's solve the equation this way. Let's write this as basically the determinant of this equation is b squared minus 4ac, which is equal to 18 squared minus 4 times a, which is 1 times negative 144. It's a positive number. So it's equal to 18 squared. This is 144. So 18 squared is equal to 18 times 18, 64. 8 plus 6 is equal to 14. 0, 18, 4, 2, 1, 324. 324 plus 144 times 4 is equal to 16, 1. 16, 17, 1, 576, 576 plus 324 is giving me 0, 801, 900, equal to 900. So b squared minus 4 is equal to 900, and so x, or basically a, is equal to negative b plus or minus the square root of b squared minus 4ac over 2a, which is equal to negative b, which is negative 18, plus or minus square root of b squared minus 4ac is the square root of, so I can write the square root of b squared minus 4ac is equal to the square root of 900, which is equal to 30 plus or minus 30 over 2a, which is equal to 2. So I can write this as take a 2 out, negative 9 plus or minus 15 over 2, and cancel these 2 out. So I have negative 9 plus or minus 15. Now 15 minus 9 is equal to 6, so that's a is equal to 6, or negative 15 negative 9 is equal to negative 26, or negative 24, I'm sorry. A is equal to negative 24. So this number is not acceptable because it's a negative number, but a is equal to 6 here. Now if a is equal to 6, over here we said that basically b squared is equal to 144 minus a squared. We said that b squared is equal to 144 minus a squared. So b squared is equal to 144 minus 36. 144 minus 36 is equal to 3, 14, 8, 0, 108. B squared is equal to 108. So b squared is equal to 108. And then so now you have your a, you have your b. You put it over here in this equation. Your a is 6, b squared is 108. A is equal to 6 and b squared is equal to 108. That means that basically using this equation, you can write y squared by a squared 36 minus x squared by b squared 108 is equal to 1. That is the equation of your hyperbola. Y squared by 36 minus x squared by 108 is equal to 1. That is the equation which is correct. Okay, so this was basically the end of the theory part that we had for these hyperbolas. We have a couple of questions here as well. There are around 15 questions that we will do that we will start in the next video. So I'll see you in the next video.